Thank you, Matthias. Thank you, everybody, for being here. I'm going to talk about stability analysis tools for microgrids, and in particular for electrified transportation systems. I'm from a University of Lorraine, as mentioned by Matthias. It is the second biggest university in France. It is the first in terms of corporate relations and the third in terms of research. We have big projects with, in particular, Safran Group. This comes from Safran Group, this work. We have other partnerships with GE, General Electric, Value, and I don't remember all of our partners, but we have big projects with very big French companies. Here is the outline of my presentation. After a short introduction, I go to small signal and then large signal stability analysis tools, and then I will conclude. First, our motivation. You know, we have several energy types in conventional aircraft, electrical, mechanical, hydraulic, pneumatic. I think you are rather familiar with these types of energy. And the thing that using many different energy sources, it causes reduced system efficiency and increased weight and volume. And for transportation systems, the second point, I mean, weight and volume is very important. So the idea is to reduce the volume and weight. First, we go through electrification. Another motivation to electrify more electric aircraft is to get them more reliable, because of electric systems. We can have some fault detection and even prognostic and so on. So the idea is to electrify these kind of systems. This comes since 10 years ago, and more people work on that, and I think you know this topic. Just a slide on a more electric aircraft. We have different actuators in the system. You have at least 2 distributed microgrids in the system because of reliability issues. You might have even more. It depends on the aircraft type. And the topic is power by wire. Replacing hydraulic actuators by electric actuators is the first step. Then pneumatic actuators will be removed also, and so on. A few examples here. Electric power can go through flight control system. We have the same for landing system. These 2 systems, they are the first 2 systems which have been electrified. Boeing, in particular, they work also on de-icing system. It's not the case of Airbus in Europe. In 787, you have de-icing system which is already electrified. Now let's focus on a specific system. As an example, here I chose this system, flight control system. You have here the flight system of A380. You have 3 ailerons. Each aileron has 2 actuators. And now at this stage, the idea is to have one electrified actuators, the other one is mechanical. For the second aileron, you have one mechanical, and the other one is hydraulic. And and for the last one, you have they combine different energy types for each aileron in such a way to get the system more reliable. But the idea is to have both actuators electrified. PMSMs are the machines that are going to be employed in these kinds of application. And here you have the powertrain. You have the motor at the end. Then you have an inverter supplying the motor and an LC filter connected to the microgrid. Actually, if I focus only on a very small part of the system, we can summarize the system to the microgrid that you can see on this slide. We have 2 actuators. We have a storage system. Then we, on the left, on this part, you have the power supply. And here you have a very small microgrid. Some people talk about a nanogrid. It's not a matter, the name. You have a DC bus distributed, supplying several loads and coming from a power supply, a DC power supply. The thing that in these applications, loads are very tightly controlled because we need good performances. So all these DC-DC converters are tightly controlled, and the DC bus voltage, this voltage is also controlled by the storage element here. Here, this storage element is a supercapacitor or ultra capacitor. But even though this DC bus voltage is controlled, the thing that you can't avoid unstable oscillations under some condition. So if you don't pay attention to stability issues, you might have an unstable microgrid. So how to analyze this stability and how to get the system stable? Even if I choose, just a very, very simple system, you have just the motor supplied by the inverter, you have the LC filter, and you have the power supply here. Each single system is stable alone. The power supply is stable, LC filter is stable, you have some damping coming from resistive term and the capacitor, and the inverter motor is stable also. When you put them together, the system could get unstable. And this result, this condition here, is pretty well known. The load power, the power absorbed by inverter motor should be less than this value. Here it is an experimental result that shows that if this condition is satisfied, if the condition is this requirement is met, we don't have any problem. And if this power load is greater than this maximum value, you have unstable oscillations in such a simple system. So the stability is an issue. We have to pay attention, and then you can stabilize. There is another topic. I'm not going to talk about that. I just focus on stability analysis. And for stability analysis, we can talk about small signal stability analysis. I think everybody here knows very well these techniques. These techniques come from linear systems. Middlebrook is an old criteria. It was published something around 40 years ago. It comes from electronic. Nyquist plot, phase margin, gain margin criteria. And the linear state space analysis tools, based on eigenvalues and so on. The drawback of these systems, we don't know the domain of validity. It depends on how nonlinear is your system. In order to get some information to that, we have to go through large signal stability. And mainly we can speak about two main families, numerical tools and analytical tools, to get some idea about domain of validity or domain of stability or domain of attraction, different names people gave to these techniques. And so the objective of this kind of techniques is to estimate or to determine the domain of stability of the system. First, let's start with the small signal stability. I go a little bit fast because I think you know very well these kind of techniques. The idea is, okay, you have two subsystems. For example, if I go back to the drive system, you have inverter motor, and then you have power supply LC filter. You put them together, so you have the front-end system, you have the load system, you put them together, and then you go by these transfer functions. And then this one is stable, this one is stable, I mentioned that. And then because of this interconnection between these systems, if you look for the voltage transfer function, I mean the output voltage on the input voltage, you obtain this kind of transfer function in which you have ZM. ZM is a transfer function appears. It is the ratio between the output impedance and the input impedance, output impedance of the front-end system and input impedance of the load system. And so if you are looking for a stable system, this ZM has to meet some requirements. These requirements come from Nyquist plot, or first Middlebrook published a very conservative way to meet these requirements. You have to avoid big gains. You have to avoid, you define a gain margin, and then if you are inside, so that's good for you, and your system is stable. Here you have the both plot of the same transfer function, and you can see here that Z in should be kept always over Z out. It should be greater than Z out. And here this curve is for a gain margin. Here it is fixed to 6 dB. And you can see here in some range, frequency range, this criteria is not satisfied, is not met. So the thing that in some cases you don't need to be such conservative, because the critical point is -10, it is here. And if you are somewhere here, even if you are in the gray zone, there is no problem for you, or here there is no problem for you. It is why a few years later, people suggested this plot coming from Nyquist plot. It's called phase margin, gain margin. And now, even if you have in this case, in this part, there is no problem, your system is stable. It is a typical Nyquist plot, so it is less conservative than Middlebrook's criteria. And then linear state space, it is pretty well known. You have a nonlinear system. The thing that most of our systems are nonlinear. You can linearize them if you neglect some parasitic terms, but actually these parasitic terms are very important. Just I go back to this slide to talk about it. For example, here you can see that resistance RF, it is just the inductor resistance here, and the equivalent resistance of the system from diode bridge and the inductor. Actually, most often it is considered as a parasitic resistance, and some people neglect it. But for the stability, it is very important, because if I replace RF by 0, my Pmax is 0. So we can't neglect this kind of small parasitic terms. That means that your system gets nonlinear. You have a nonlinear system, so you have to linearize it around an operating point, and then it's very well eigenvalues and so on, and then you have a necessary and sufficient condition of asymptotic stability without having any knowledge about the domain of validity of your analysis in that case. A short comparison between eigenvalue analysis and phase margin and gain margin. You can see here that in red line here, it's the domain of stability in terms of P1 and P2. P1 and P2, these are powers absorbed by first load and second load. They are called first and second load. And you can see that the dark blue part cannot be taken into account if you use, for example, Nyquist plot. That means Nyquist plot is a little bit more conservative than eigenvalues analysis. So let's conclude on a small signal stability analysis. Once again, you are familiar. This is why I don't pay my time on that topic. First approach is based on impedance specifications. The good thing with this approach that you don't need a complete analytical model. Even we have authors propose online identification of input impedance or output impedance of each subsystem. So you don't need to have a detailed model. That's a good thing. So the experimental data can be used in real time and online manner. But the thing that, the phase margin, gain margin is a little bit conservative, so you underestimate the stability domain. And the state space model, what is good, that you have sufficient and necessary condition, but the bad thing that you need a detailed model. Now, let's go to large signal stability analysis. And first, you don't need to linearize around the operating point. To estimate the domain of attraction, as I mentioned, you have numerical methods or analytical methods. The analytical methods are mainly based on Lyapunov theorem. Numerical methods, you have, most frequent use methods are numerical solution of state equation and inverse trajectories. Just an example with the first one, numerical solution for this system. This system, it is the same. The load here, it is the inverter motor. You have the LC filter, and here you have the DC power supply. And using the numerical solution of the state space equation, you get this kind of plot. Every red point here corresponds to a stable point. That means if you start on that point, you go to the operating point. The operating point here is 0, 0, because you translate the operating point to the center. And every dark point or every black point here, it is not in the domain of attraction. That means if you start somewhere here or somewhere here, you go to infinity. But the thing that for every single point here, we had to simulate the system. And it's very time consuming. And at the end, you got a result that depends to all parameters. If you change only one parameter in the system, you have to start all these simulations. The domain of attraction, now you had a plot showing that. But what is the physical meaning and what is the interest for example, Airbus or Boeing? The things that we have some standards in aircraft. For example, Airbus asked Safran Group, in which we work, with whom we work, that when you have a load step from 0 to full load, you have to meet these requirements. You have to not exceed this voltage, and you have to converge to operating point in less than 30 milliseconds, and so on. So these requirements, they are directly related to the domain of attraction. Here you can see that this domain of attraction, the red one, for example, covers very well a square. Each side you have delta V. So if that's the case, so you can give the guarantee to your client, for example, to Airbus, that this system is stable and we can meet this requirement. Now, how to estimate this domain of attraction without simulating, without going through numerical methods? If you use Lyapunov function, so the first step, you need a Lyapunov function candidate. Then you have to derive the stability conditions coming from this derivative should be negative. And then this condition is verified in the domain, and this domain is the domain of attraction, at least the estimated domain of attraction. How to find a good Lyapunov function? Several techniques, you can find them easily in textbooks and in the literature. For a linear system, it's very easy. For nonlinear system, it gets a little bit more difficult. We have several techniques here. As I don't have enough time, I go just to the last one, multiple modeling. What is the multiple modeling of nonlinear systems? That means that each nonlinear system, or not each, under some conditions, nonlinear systems could behave as a linear system if you are in a restricted area of the state space. For example, here you can talk about linear model 1, then linear model 2, 3, and 4, and then you can have a weighted sum of all these linear models, local linear models, and these weighting terms are nonlinear. So you push all nonlinearities to the weighted to weighting factors. Here you have some mathematical backgrounds on that. Your system is written under this form. You can write it under this form. A is a matrix, but it is a nonlinear system because this matrix depends to X. And if each linear system can be defined, with this model, it is an autonomous model in which AI is a constant matrix. In contrast with AX, which is a variable matrix. And if you can write your AX as a sum of constant matrix multiplied by mu functions, and these mu functions are called activation functions or membership functions, then you get your multiple modeling. This kind of modeling that I'm talking about, they are called Takagi-Sugeno modeling, multiple modeling. We have other multiple modeling. It's only one of them. And the number of linear local models depends to the number of nonlinearities that you have in the matrix A. I mean, if you have a term in matrix A depending to X, that counts for one nonlinearity. If another element depends to X, that is the second nonlinearity, and so on. And you can see here that the number of local models grows fast with the number of nonlinearities with this relationship. And why we have 2 power k? Because each nonlinearity is replaced by its minimum value and maximum value in the domain you are studying. But the good news is that you don't need to identify all these nonlinear weighting factors if you are looking for the stability. So forget the nonlinear weighting factors, just focus on a AI matrix, and if you can find a positive definite matrix M satisfying this LMI, so your system is stable. Now, an algorithm allowing us to define a domain D in which this LMI is feasible. Here you have this algorithm. You start with a 0 domain, and then you try to get a wider, larger and larger domain. And if your system, if this LMI is still feasible, you increase a little bit your domain, and then at the end, you arrive to a point that this LMI is no more feasible. In that time, your domain of validity, or your domain of stability, sorry, is the last domain you got. Here you have a script, MATLAB script for the very simple system. For microgrid, you need much more lines in this script, but the main idea is the same. Now, I will show you just 2 or 3 results, and then I'm done. First, estimated domain of attraction of the same system that I showed to you. Here you have several domain of attractions, just to compare it with the numerical domain of attraction that I got a few minutes ago. And you can see that this domain of attraction in a red line is conservative. That's the cost to pay because with this algorithm, you have your domain of attraction in a few seconds. With the numerical tools, you need several hours. And changing a parameter in the system is very easy with this algorithm. So you change a parameter, and then you see the result. But it is a Lyapunov-based approach, so you are conservative. Now, last result on flight control system. The good news that with this approach, you have a closed form. You have an equation giving you the border of the domain of attraction. So you know very well what is the border of your domain of attraction, and you can see if you are inside or outside of this domain. And if you are interested in, you can plot graphical form of the domain. You know, if you go to 3D plots, you got this kind of cheeseburgers, or you know, it looks like McDonald's, but you know, it's the domain of attraction in 3D. By the way, here in this system, you have, 8 or 10 variables. I don't remember the number of exact variables, but you can't plot it in 10D. So you have to project in 3D, and you got this kind of plots. Now let's conclude on large signal approach. They are based on Lyapunov function. Advantage that you have sufficient conditions. They are not necessary. That means if you are not inside the estimated domain of attraction, you can't say that you are unstable. The only thing that you can say that you don't know. But if you are inside, it is sufficient to get inside, and you know that you are stable. That's the good thing. And in matter of instability things, better you stay a little bit conservative with that. And you have the formal equation of the boundary of the domain of attraction. The drawbacks that you are conservative, you have a smaller domain of attractions than the actual domain of attraction. And now the main conclusion. 3 points. Stability analysis tools. When you have high power loads or small DC bus capacitance, you need to to analyze the stability. When you have tightly controlled loads, they contribute a lot to instability. And because of resonance in LC filters, you have oscillations. What tool do you use? You can use small signal tools for local stability, large signal for domain of attraction, and I didn't talk about that because I didn't have enough time, but even you can have discrete time tools in the case that your LC filter cutoff frequency is very high, it is comparable to the switching frequency. In that case, average modeling is no more valid, so you have to develop other tools, and I'm talking about discrete time tools. And how, you might have database analysis or model-based analysis. I talked about them, so I'm not going to develop them. Otherwise, if you have some questions. Thanks for your attention.
Okay, we have time for maybe one question.
Thank you. Could you maybe explain a bit, for those of us that are not on stability, what methods can we use in real time? What do you choose between small signal, large signal?
Yeah, in real time, the most frequently used technique is based on online identification of input and output impedances, and then to check if the stability is verified, the requirements are met or not. Otherwise, people now implement active stabilizers more and more. I didn't talk about that, but in most cases, in particular for aircraft applications, active stabilizers are there not to stabilize the system, in its normal operating point. The system is designed to be stable. The only thing that if, for some reasons, for example, you have a faulty capacitor or other thing in the system, and your system gets unstable, the active stabilizer, it is an online approach that it stabilizes the system, so we can talk about a safety measure. So that's the case for Saffron Group, for example. Yeah.
Okay. Thank you, Babak.
Thank you. Thanks so much.
Once more.
Thank you.